So let's get into the main topic. So we're going to continue our discussion of pipeline parallelism. And, basically this is, the third kind of major class of parallelism that we're covering in this class, and the last one that we'll be covering. And, we talked earlier about request level parallelism. So if you have a big service that you're offering and lots of people are sending in requests simultaneously and those requests don't depend on each other, then you could do those all at the same time. And we talked about that in terms of cloud computing. And, this is kind of what's bringing Siri down at the moment. Too many requests coming in all at once. We talked about data level parallelism, and we talked about that at sort of two scales. One was, again, kind of the cloud or cluster scale, which was MapReduce. The other was on a single chip, and actually a single processor, the SIMD types of programming. And what we're talking about right now is instruction level parallelism. We've actually seen two versions of this. One was the multi-core version. So, the fact that on a single chip you'll have multiple processors, and if you do things the right way, you can get those. You could be running multiple instructions at the same time. And then we've been talking about, most recently, pipeline parallelism that says even with a single core, if you set things up the right way, you can get multiple instructions happening at the same time. Okay? So remember that our measure of performance is this metric, cycles per instruction. And when we introduced that, the idea was to run a single machine instruction, how many clock cycles did it take? And we talked about, bringing that number down. The way you bring that number down is through parallelism, okay? So what we've been talking about is the MIPS version of this, which is this 5-stage pipeline, and we're going to try to run all 5 of those stages at the same time. So, going back to the picture we saw in the first class, these are all the different types of parallelism, and we're basically right here, okay? So we're focused on that part. And again, that's because we sort of started at the top, came around from the bottom, and we met in the middle. And that's where we are right now. All right, so last time we introduced the idea of parallelism, we gave this great laundry example, which, in fact, the book seems to be quite enamored with. They use it through a lot of the chapters on pipelining. And the basic idea that if you had a series of steps you needed to do your laundry, and each one required a different resource, that to make things go faster, rather than just having one person doing their laundry at a time, you could have multiple people doing their laundry and try to keep all the resources busy, okay? And so that was the laundry version of it. The way we implemented that was we put registers in between the different stages of the data path, and then that's what allows the different pieces, the different stages to run at the same time, okay? And those registers keep the state, as a given instruction is moving from instruction fetch to decode to execution to data to memory write, those registers are keeping that state that they need to make sure the right things happen. And so what you're passing through there is, the instruction as well, or things that you've obtained from the instruction, plus any data that you need to flow in order to make sure that you set the control signals the right way. So remember, what's going to make our processor do what it's supposed to do is the correct firing of the control signals. And now that gets a little more complicated because we've got to make sure that the right signals are also being pipelined. And so we're not going to talk about that so much today. We'll probably talk about it more on Wednesday. All right? But anyway, another way to look at pipelining, if you're not thinking about laundry, is this way, where basically we're going to take our 5-stage pipeline, and as soon as one starts, we're going to start the next one, then the next one, the next one. So at any given time, we have a bunch of stuff going on, okay? And so this is, fetch, decode, execute, memory access, and write back. Okay, so we're going to try to get all those going as much as we can. All right, and this is the picture we saw with the registers. And again, it kind of looks like that. If you think about this as sort of a schematic of our data path, then the instruction fetch, fetches from the instruction cache, decode happens, reads the register file, execution uses the ALU. Memory, of course, uses the data cache. And then if we're doing a write back, that goes to the register file again. So this is a little bit of a schematic so that when we look at the pipelining, we can see which resource is being used by which instruction. All right, and then we'll see what that looks like here. So this is another view of this pipeline type of execution. And the idea is that when we're reading from a resource, the right half will be shaded. When we're writing to a resource, the left half will be shaded. Okay, and here we have the register files highlighted that way. And yeah, and so you can see that at this stage, if we had these 5 instructions running, in this stage we have everything working at the same time. We have all 5 resources being used. Okay, and the other thing you see here is that there's a startup where you have to fill the pipeline, and steady state, you want to be in this region as much as possible. You want to have as much going on as possible. Okay. All right. So last time we looked at this picture and we said, okay, if we were doing what we were doing originally, the single cycle processor, there was no pipelining, and so basically, if you were this is the cost of doing a load. This is the cost of doing a store. This is the cost of doing an R format instruction, and so on. And if you were running instructions one at a time, then your clock tick would have to be long enough so that your slowest instruction could finish, because at some point you'll be running one of those slow instructions. Okay, so if we did it this way, we would end up running with a clock cycle of 800 picoseconds. Okay, and that's what this is a picture of. So we run one instruction, then we run the next instruction to completion, then the next one. In the pipeline scheme, we can get that down to an average approaching 200 picoseconds, because that's the time of the longest stage that we have. So if you pipeline, your clock tick goes down from the longest instruction end to end to just being the longest stage, okay? And yes, instructions are going to take more ticks. They're going to take more cycles here, but the clock's going to be ticking faster, okay? And in this case, it ticks, at 4 times faster, all right? The other thing you'll notice about this is that there are some stages that don't take as long as others. So for example, reading the register file. So there's just a little blank space in there. And that's because, again, the clock tick has to be long enough to handle these longer stages, like the ALU, for example. All right? So, but that's the game we're playing. We're trying to get that clock to tick faster so we can get stuff to all happen at the same time, so we can shrink the amount of time it takes to do a lot of work. Yeah? If you're not doing all the same instruction, like you have different types in your pad and
Yep.
would we have to make the clock cycle like the longest of any of them, like no matter what instruction it is? Okay, yeah. So the question is, if you're running different instructions, let me paraphrase it, like a load in a store versus an R type or something, does that change how fast the clock is going to tick? And the answer is yes, but maybe not for the reason you're thinking. So here, remember, in the single cycle approach, the reason that a load takes the longest is because it uses all 5 pipeline stages, right? And a store only uses 4 of them, right? And some of the other instructions only use 4 of them. Okay, so that's the problem there. Once we've gone here and we break these things up into these little pieces, then we don't actually care at this level what instructions they are, right? We have an instruction fetch, we have an ALU, we have register access, and so on. And that's all we care about. We don't care what instructions that they're from. Now, there is another problem, though, and that is that you can't necessarily, in our current design, pipeline all the instruction sequences, right? And there are these things called hazards. That's what we're going to talk about next. And that's where you care about what the instructions are. All right? Any other questions about this basic idea of pipelining, though, before we move on? Yeah?
Isn't data access supposed to be really slower than the other?
Yeah, okay, good. So isn't data access supposed to be really slow? And the answer is, yeah, exactly. And if you see the way we draw the data access here, we don't actually show it going to memory. We show it going to the instruction cache or to the data cache. Okay, and that has to be fast, right? Level 1 cache has to happen within, it has to be fast enough to return within this clock tick. Okay, so when you get into trouble with memory access, isn't in the normal case when you get a hit in the L1 cache, it's in the other case when you get a miss in the L1 cache, and then that's another type of hazard that we'll talk about. Okay, that actually, you have to figure out how you're going to wait for that one. But in the normal case, when you're getting hits in the cache, there's no delay. You can keep going. All right? So that's an important thing to keep in mind. When we say we're going to memory, we don't really mean that. We mean we're looking in the cache, and then only if there's a cache miss, we look in the next level, and only if it's not there do we find, level 3, and then finally go to memory. So we try everything we could do to avoid going to memory. But level 1 should return within that, 200 picosecond budget. Okay? All right. So if all the stages are balanced, meaning if all our stages were exactly the same length, then if they all take the same time, then our speed up would, the time between instructions, so the amount of time it takes to execute an instruction on average is, in the pipeline case, is basically what it was in the non-pipeline case divided by the number of stages. Okay? So in other words, if it used to take you, 1,000 picoseconds to execute the entire, or 800 we had in the entire instruction, well, that's going to be hard math. So we'll say 1,000. Okay, and you had 5 stages of 200 each. Your average time to execute instruction should be 200, right? Because in a space of 1,000, you'd be able to execute 5 instructions. Okay, but that's only true if things are balanced. Yeah. So we're not neglecting clock to queue and hold time. So that's an important. That has to be factored into the clock tick. Yeah. So you have to be able to finish, from when the clock starts, clock to queue delay, make all that work. Yeah.
Well, if we put registers in between, wouldn't that add some time? So it wouldn't actually be.
I see what you're saying. Yeah. So this is being a little sloppy. It's a good point. When you put those registers in between the stages, you are introducing a slight delay because remember, there's registers have setup and hold time, and then they have clock to queue delay, and so you have to factor those in too. So that's right. So this is sort of best case, and with the registers, it's probably not even the attainable best case. Yeah.
But it wouldn't be the summation of all the clock to queue delays just be one of them. It's going to be all the same registers. Would it be? Because otherwise, each cycle you have like a chamfer, right? Each register with a chamfer information and taking the node information.
Right, but each cycle, each stage, has to read from the register that's its input and write to the register that's its output. So that'll be, so if it was 200 before and it takes 10 to do this other stuff, then now it's become 210. Yeah, yeah. And there may be some ways to overlap that, but it's going to introduce a little overhead for sure. All right. All right, if it's not balanced, then you're going to, you're not even going to do this good. Okay, so for example, in the case we looked at, we started it at 800, we ended up at 200, even though we had 5 stages, and that's because some of the stages were shorter than others, right? We had these 2 100 picosecond stages, okay? And the other thing to remember is, from the time it takes you as an instruction, from the time you show up to the time you get executed, that doesn't change, right? So the latency, the amount of time it takes to execute a given instruction hasn't changed. In fact, it's arguably gotten slightly worse, okay? But since you're doing everything in parallel, since you're doing a lot of stuff in parallel, the average speed, the throughput, is going to get much better, okay? Because again, you'll be running 5 instructions at a time, okay? So, but that's just, to keep in mind this morning. Okay, so all of this works great until you actually start looking at the particular instructions you're running. Because as we saw last time we started talking about, there are dependencies among instructions, okay? And there's really 3 classes of dependencies we're going to focus on. I'm going to go through 2 of them today. And then on Wednesday, we'll do the last one. I might introduce the last one today, depending on how time goes. So the first type is called structural hazards, okay? And basically, that happens when a resource you need is busy, all right? The second is a data hazard, and I'll, of course, go into more detail on these. Data hazard is actually one that you guys picked out already last class when we first started talking about this, which is, you know, if you're doing an operation that loads a register, okay, it takes that register doesn't get loaded, you know, until the end of the last, operation, right? Either you know, from the ALU, you know, basically it doesn't get the register doesn't get updated until the write back phase, okay, which is the last step. So any instruction that's kind of one step behind that instruction wouldn't be able to see the register write, okay, because it hasn't even happened yet. So that's called a data hazard, and we need to talk about that. And the example there, so I guess the structural hazard is, you know, you want to put your laundry away, but your roommate is studying, and you don't want to disturb your roommate. That one's probably not very realistic. This one may be more realistic, which is somehow your socks got separated into two different loads, and you're not done until you've gotten both of them. That's a data hazard. And then a control hazard is, you know, remember, we've got a bunch of instructions, and we're saying, okay, start this instruction, then start the next one, then start the next one, then start the next one. But a lot of times we don't know what the next instruction is really going to be because we have conditional branches, right, or jumps and things like that. So a control hazard is one where you've loaded up your pipeline, but you have the wrong stuff in it because you had a change in the direction of the program, okay? And one of the most typical times this happens, it turns out it happens a lot, because if you think about it, think about like a loop, okay? So a loop, you know, you start at the top, you go down, 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 down. When you get to the bottom of the loop, most of the time, what do? You go back up to the top and go again, right? And only once do you actually go through to the bottom, okay? So if your normal prediction, if your normal guess is, I'm going to do this instruction, then this instruction, then this instruction, then the next instruction, most of the time for a loop, that's going to be wrong, because really what you end up doing is going back to the top. So that's another type of hazard. That's another type of control hazard, okay? So these are all things that can mess up pipelining, and not surprisingly, we have solutions for many of them. Otherwise, we wouldn't use pipelining. So let's talk about how we solve them. Okay, so structural hazards are you know, maybe the easiest to understand. And the idea is if you needed, if two different instructions needed the same resource at the same time. So for example, let's say you have to go to memory, okay, to get an instruction, and another, right, so that's instruction fetch, and another instruction maybe, say, is doing a load or a store, that has to go to memory to do that read or the write, okay? Now, you can't do those at the same time unless you build your hardware carefully. And so what we really do is we solve that one just by saying, okay, we're going to have two resources, right? You might have wondered, why do we have two different level 1 caches, okay? And there were really two reasons. One is locality, right? That the L1 cache tends to have the instruction cache tends to have one form of locality, right? Because you follow the instructions in a certain way. And the data cache has different types of locality because it's all about how you're navigating structures in memory, all right? But the other reason we do it is to solve this structural hazard problem. So if we have a separate interface to memory for instructions and a separate one for data, we can then now use them at the same time, okay? So if I've got one instruction that's in the fetch stage, I've got another instruction that's in the memory stage, now all of a sudden they can both run at the same time, whereas if we only had one port into the memory, that wouldn't work anymore. Okay, so we use our split L1 caches to make that happen. Okay? All right, so the way that looks in our pipeline diagram, where are you going to get into trouble here if you didn't have, well, see, it doesn't even look like there's a problem here because we've already split them up. So here, for example, right, once the first instruction is in its memory phase, and the next instruction, that's in the fourth step. So in the fourth instruction, you're going to be going to get the instruction out of memory. Okay, and if you didn't do anything smart, that would be a conflict. So that's an example of a structural hazard, and it's one that we've already fixed before we even talked about pipelining, for other reasons in addition to this, right? The locality reason. Okay, so where else might we get into trouble here? So look at that picture. Where else do you see a structural hazard? How would you go about detecting a structural hazard? Well, yeah, go ahead. Yeah, so in the next one, look what's going on. We're accessing the register file twice, and then we're accessing the register file twice here as well. Okay, so we haven't solved all of our structural hazards yet. We still have one on the register file. So let's solve that one. Yeah, so here's one. We actually have two, okay, but this is one. Okay, so what's going on here is that what's happening here to the register? What are we doing to the register here? We're storing the value, right? This is a store word, so we're taking. That should be a load word, shouldn't it? Okay. Anyway, we're in this step. We're writing into the register. Okay, that's an interesting one. Okay, and what are we doing here? We're reading from the register. Okay, so that gives us a little hint on how we can solve this problem. Basically, we want to build a register file. Well, we got two choices. One is we could build a very, very fast register file. Okay, and remember, we've got a clock tick that's going to be determined by the longest phase, right? So figure that's the ALU, or maybe going to memory, or going to the cache. So if reading and writing the register file is each less than half of that clock tick, you could be clever and maybe do the read in the first half and the write in the second half, okay, or vice versa, okay. So maybe one way to fix this problem is to do have very fast register access, okay. The other way to do it is just to design the hardware slightly different, so that you can read and write, so that you really can read and write the registers at the same time, okay? And in either case, the bottom line is you've built the system in a way that you can do a read and a write in the same clock cycle, and then that gets rid of that structural hazard, okay? So in our fairly simple 5-stage pipeline here, we had two hazards. One was around memory, and we split that up by having a separate instruction cache and a separate data cache. So we can look at instructions and data at the same time. And then in this one, we had the register file, and we fixed that one by building the hardware in such a way that we can read and write the register in the same clock tick. Yeah?
Why is the second one a solution when you want to read and write the same register?
Yeah, so the second one, I was wondering that too as I was saying it. So, how do you build this register file with independent read and write ports? I assume that there's a way to build the circuitry so that works out okay. But yeah, you yeah, I mean, the question is where's the logic for doing that? So, but yeah, it would seem with this one, the second one, you got to make sure if you're reading and writing. I mean, it's obvious how it would work if you have different registers, but if it's the same register, what do you do? And so you got to get the circuit to do that. Yeah.
Can you go back to that picture? Yeah, that one, if that string was a load word instead of a store word,
Yep.
the register only gets to have the loaded word value all the way to the very, that fifth step.
Yep.
So if instruction one was going to use that register, it has to obviously assume it
Yep. Yep. Okay, so the comment there was, hey, look, if this is if instruction one needs the result of this load word, let's say it was a load word, this ain't going to work. And you're right, that's a hazard, but that's a data hazard. That's not a structural hazard. So that's what we're going to talk about exactly next. Okay. If pipelining was easy, we would have just taught it to you that way, right? It took people a while to figure out how to get this stuff to work. Okay, any other questions about this stuff, about structural hazards? Because I think that's all I got. Okay, So let's move on to this next type then, data hazards. And here's an example. So, here's 5 instructions. We're going to, add what's in T1 and T2, and we're going to put the result of that into T0, and then we're going to use T0 in 4 subsequent instructions. Okay? So clearly, we've got an issue there because, as you just pointed out, if we wanted to pipeline these guys, we can't. It's not until the 5th stage is done that we actually have what we want in T0. Okay? So, so how would you solve that? Well, let's see where we get into trouble, I guess. So here's our 5 instructions, the ones I just showed you. Okay? And is anything okay here? Okay? Are any of these instructions going to work well as is? And I'll give you a hint. It's color-coded. Yeah. So this one actually works okay. All right? Because why? Because by the time you have to read the register for the XOR at the bottom, the register has been updated by the add. Okay? So the value from the add is safely in T0 by the time XOR needs it, right? And why is that? Well, because there's, 3 steps in between. Okay? So we're not always in trouble. We're just sometimes in trouble. Okay? And when are we in trouble? We're in trouble when you draw one of those arrows and it goes backwards. Okay? So here, the subtraction needs the value from the add in its 2nd stage, but the add isn't even completed then. It's being done in that stage in the ALU. Okay? And, likewise, these instructions also need what's in T0, and it's not there yet. So anytime you draw one of these diagrams and you end up with arrows pointing backwards, you're in trouble, right? Because it means you're trying to go backwards in time, and it doesn't work. That's a data hazard. It's exactly what you were pointing out. Okay? So how are we going to fix these? What are our options for fixing data hazards? Anyone want to come up with something? Yeah. Okay, so you could you could sort of get rid of pipelining. Yeah. Yep, you could do, okay, so the second suggestion was you could do, if you detect this kind of a data hazard, you could put some instructions in between this statement and that statement that don't rely on the result of the first statement. And that might work. Who's going to do that, by the way? Hopefully the compiler. I don't want to write that code. Anyone else who doesn't usually, I'll get to you if no one else wants to volunteer something. Anyone else? Come on. You just made me, okay, go ahead.
I was thinking that you could just make this switch with eliminate pipelining if it does depend on T0, and then just pass on the job to the compiler to optimize as much as possible to not have a sort of backward flow.
Yeah, so it's right. So you want to, right, you can do sort of both of those. You can let the compiler put some harmless statements or move some things around, as long as it doesn't change what the program's doing, right? Because that's called a bug. If your compiler changes the meaning of your program, that's called a bug. Okay, so it's called a bug in the compiler. So so there's a way to combine those. How about any EEs in the audience? Any way? So let's look at that picture. Any other ways we might be able to fix this problem? So everything we just talked about was mostly software. Yeah?
Instead of taking the results in the register, you take it in the
Yeah, awesome, right. So it turns out, do we know, let's see, where do we know we're adding, we're going to skip that step. So it turns out that right here, we actually know the result of the add, okay? So for the cost of one wire, I could probably solve my problem, okay, or maybe multiple wires. Okay, so this is called forwarding. Okay, so I can actually change my wiring in order to solve these kinds of hazards. You got to get the control to work properly then, but you can do it. Yeah?
Yeah, that's not just the wire. There's also a mux.
There's a wire, and whenever you have multiple wires coming to the same place, you need a mux. Whenever you have a mux, you need a control signal. you know, it is more time for the stage, but that stuff's really fast. What's tricky is you got to make sure you get the control right. And the control is going to be driven by those things that are in those registers. So it's going to get a little trickier. Yeah. How would you do? Well, we'll get there. We're going to do the load case after this. Yeah.
That's something to fix with side with the sub.
With the sub, yeah, that's probably not going to work for the sub. So, you know, there's no rule that says you only get to use one solution. Okay. So, you know, we're gonna try to, you know, we'd like to keep things simple, but there will be cases where we come up with a solution that works for some cases and not others. And then we, as chip and instruction set designers and compiler writers, will figure out, you know, how many of these little tricks we want to try to play, and we'll do it based on how likely we think a particular hazard is to happen, right? If it's a hazard that hardly ever happens, then you're probably not going to do a lot of work to fix it. But if it's something that happens all the time, like I was talking about that branch misprediction, where, you know, when you get to the bottom of the loop, most time you go back to the top, you want to fix that one because it's so common. So we're going to combine a few of these. Okay? Yeah.
How does the control work with respect to the control takes instruction bits and uses that for control
Yep.
messages, but then if you have another instruction coming in,
Yep.
how does that get all like stalled?
Yeah, so the question was, how do we get control to work in this thing? Because before we built this nice controller, we had, you know, God and man meet, and everyone was happy. But now we've got all this stuff going on at the same time. How do we do the control signals? And the answer is that those registers, the answer is I'll talk more about it on Wednesday. But the short answer is we're going to drive some of those control signals from the registers, not from the original instruction. And we're going to have to carry along enough information into those registers in between each stage so that we can get the control signal to happen at the right time. Okay? So way in the back, yeah?
If you're leaving the solving of some of these hazards to the compiler, doesn't that mean the compiler is going to need to handle it differently so basically every machine gets mad?
Yeah, so it is a complexity. It's a little bit of a complexity for the compiler writer, for sure. And, you know, so compilers, you know, are written in a modular way so that you separate out the things that are you know, processor dependent. But absolutely, and in fact, the MIPS, it's an interesting point. You know, remember, the MIPS processor is based on this reduced instruction set, which basically said, I'm going to make my hardware really simple and kind of dumb, and I'm going to push a lot of that complexity, a lot of the thinking up to the compiler. And this is just another example of that kind of decision. There are other ways to do it. You could make the hardware smarter, but then the hardware gets more expensive and maybe slower. Yeah. Is there any reason to not always forward? Well, so we're going to set it up so you are always forwarding. And then, as was said earlier, there's going to be a MUX, and you're going to just have the control tell you whether you read what's coming in from that forwarding or not. So let's, anything else? I thought I saw another hand. No? All right. So let's look at what that looks like. What we're going to do is we're going to do exactly what was said earlier, which is for these guys, we're going to read the results sort of directly from the ALU. Okay? So we're going to forward there and there. That's going to be a little tricky. We're going to have to do that through a register. And then this one is tricky with the OR because that's actually in the same cycle. But remember, if we make our register fast enough so that we can read it in the first half and write it in the second half, we can actually get that to work, right? Because that's a read and that's a write. Okay? Or no, I'm sorry, that's a write and that's a read, sorry. But you can see that can happen, then this can happen in the same cycle. And then we're going to forward here. Okay? So we've got sort of two tricks. One is this extra wire, and the other is in a single cycle, we can do the transfer within the register file. Okay? Because the read and the write each takes half a cycle. Okay? So that's forwarding. The other type of data hazard is, was already mentioned, which is, well, what happens if you have a load word in here, okay? Which I think we did anyway in that previous example, but I have to take a look at that again. You know, again, so if we're loading something into T0 and then we want to use it in the next instruction, we can't do that even with forwarding, okay, because it's just not ready yet. So you can't go backwards, even with forwarding. So What we do there is we introduce what's called, well, there's a couple things we can do. We can stall the pipeline, okay? So this is called an interlock. And basically what this says is if the hardware detects that we're running this instruction, it's going to stall the pipeline for one tick before it lets anyone else do anything else, and then forwarding works, okay? So this is called an interlock. Now, interestingly, MIPS doesn't have an interlock, and in fact, they were so proud of the fact that they don't have an interlock, and I'm sorry this is getting blocked a little bit, but basically MIPS is an acronym, you probably guessed that, and it stands for Microprocessor Without Interlocked Pipeline Storage, okay? So, and again, this is because they said, yeah, it would be nice if the hardware did this, but it would slow down the hardware and make it more complex, so we're not going to do this. And that means you, Mr. or Ms. Compiler Writer, have to make sure you get this right. And that's a decision. If you're going to write a compiler for a MIPS processor, that's something you're going to have to deal with. Okay? Now, does anyone know MIPS is actually it's a bit of a pun? Because back in the day, the way you used to, before clocks started running at gigahertz speed, the way you would measure the speed of a computer is how many millions of instructions per second it ran. And that was what MIPS originally stood for. When these guys created this, this processor, they probably didn't think that that acronym was, that years later nobody would actually know what MIPS originally stood for, because processors are so much faster than that now. Okay? So, but anyway, so this is a big architectural concept. A lot of systems do have this interlock. It's just not the one we're studying. So the way to think about it is there's a slot after this memory delay, right, after this load delay. So we're going to call this the load delay slot. Okay, so if you have a load word instruction, the instruction right after that is called the load delay slot. Okay, and the question is, what do you do with that load delay slot? Okay, interlock says, don't worry about it. You can put whatever instruction you want there, because I'm not going to let anyone run anyway. I'm going to make everybody wait one tick. Okay, but if you don't want to do that, then you got to be a little clever about what you put in that load delay slot. Okay, so one thing that would be cool would be if you could take an instruction that you were going to do anyway and put that in that slot, right? As long as it's not dependent on the result of that load, right? You can put anything you want in there. Okay, so that's one thing you might want to do, is put a different instruction in the load delay slot. But what else could you do if you wanted to mimic that interlock thing? What could you put there? If you were a lazy compiler writer, what would you put in the load delay slot? Yeah, and what's an empty instruction called? Yeah, no op. Yeah, so if you ever heard somebody say that someone else was a no op, this is what they mean. It's an instruction that doesn't do anything. Okay, so you could put a no op in there, which is an instruction that's just going to eat up some clock time, and then everything will work. Okay, so to get to your question up in the back there, yes, this adds some complexity, but it doesn't have to be that complex. You can always, every time you generate a load instruction, put a no op right after it. And then anything you do after that is just better, right? So that'll work, that's correct. And then you can think about being smarter about putting other instructions in there and getting things to go faster. Okay, but in order to get something to work correctly, it's not hard. But then you want it to go faster, then you can be smarter. Okay, and if you're too smart, you break it. That's kind of how it works. Okay, so what happens there, so if we put a no-op in there, effectively what we're doing is we've got, bubbles all the way along, and we end up getting the behavior that we wanted. Okay, now we can do our forwarding trick, and things are going in the right direction. Yeah? Okay, so where are the checks? So there's going to be, so there's a couple answers to that. One is, for a lot of these things like forwarding, you don't actually need a check. You just need to make sure that the control bits get set correctly. So that's okay. That just will happen in the wiring when we build our control logic. well, that's going to make sure that those control bits get set. So there's no checking there. For this kind of stuff, for the interlock, there's no checking necessary because the hardware itself enforces it. And for the stuff we're talking about here, like you have to put a no-op in there, there's no check. If you get it wrong, there's going to be a bug. Okay, so it's that combination of, the control does it for you. The hardware is going to do it for you, outside of the control. It's just going to stop the pipeline for a little bit. And, sorry, it's up to you, the compiler writer, to get it right. Yeah. The register write is happening, so we're loading, we're getting stuff from memory. And we're loading into L2. Yeah, you're right. It seems like we're off by 1 here, right? So we want to read. At this point, we're going to have the address. We're going to read from memory. I guess the question is, we're going to forward from here. Sorry, we're going to forward from here to the ALU. And then we do have to do something to make sure that it works correctly. But we don't actually have to write the register. We can forward to the ALU here. And we can write the register here if we needed to. So I think we can get it to work, but I agree, you need to draw the arrows in correctly here. Yeah?
So you could just have a mux to choose between the register read and the forwarded value and put that into the ALU?
Yeah, so you have to, remember, anywhere that there's a choice, so you'd either be getting something from the register or from the ALU, there's going to be a mux there, and there's going to have to be a signal that controls that mux. Absolutely. Yeah? That signal is going to come from the, it's going to come from the, it'll be driven by what's in that register of the previous stage. Okay? So basically, forwarding isn't going to be yes or no. Every instruction, it's going to be forwarded or not forwarded. Yeah. Yeah.
Wouldn't it have to be in the control because you also have to check which register you have access to, not just that you're accessing the register?
Yeah, so we'll talk about control more on Wednesday, but what we're going to do here is we're going to change control to being, once per that big clock, to now it's going to be each control signal is going to be driven by one of those intermediate registers. And you have to drive the right control from the right register. Right? The correct control line gets driven by the correct register. So we'll look at that a little more next time. But absolutely, we're basically taking the control apart and doing it, in between stages, not in one big controller like the one we built last week when we, put everything together. This is going to be a little more complicated. Basically, every stage has its own control that's driven by the register for that stage. Okay? And the book does a pretty nice job of going through this, by the way. Nicer than I'm doing. Okay, so some things about the instruction set. We've actually already talked about most of this, but the fact that MIPS has all the instructions as being 32 bits makes it easy to figure out what's going on. Other processors like the x86 has all sorts of, they have 1-byte instructions, they have evidently 17-byte instructions. And you got to figure out how to pull all those apart in hardware. We don't have to do that because every instruction is 32 bits. The high order 6 bits of the opcode, the low order 6 bits, if the opcode's a 0, are going to be the function code, and that's kind of how it works. Okay? And so that makes it really easy to do decoding and reading registers, and we can in fact do it in one step. You wouldn't be able to do that if you had a much more complex instruction decoding. It would take longer. So, there are things like that going on in the MIPS architecture that make it this kind of simple 5-stage pipeline. But you might, in a more complicated processor, have more pipelines than that. More stages, sorry. Okay, the third type of hazard is called a control hazard. And I'm just going to tell you about, I've already told you what it was. I'm going to go into this in more detail when we meet next time. But basically, the problem is if you have a branch, say branch on equal or branch on no equal, and you're loading up your pipeline, you don't actually know until you execute that branch where you're going. Okay, so things you might have started processing in the pipeline might actually not be instructions that you're going to run. Okay, or alternatively, you could just not load the pipeline until you get to the branch, okay, and know what's going to happen. But then that's unfortunate because there are a lot of branches where 99% of the time you'll take the branch and 1% of the time you won't, right, or vice versa. So it's kind of a lost opportunity. So what we're going to talk about next time is how do we fit branches into this architecture? Okay, and that's kind of a hint. I was going to do peer instruction, but as usual, I've run out of time. So look at this, think about the answer. I'll try to show you a couple peer instructions next time. But yeah, I'm sorry about that. I got closer this time than I ever have. But we'll do it next time. So we'll see you guys on Wednesday.